For those of you who I have not yet had the pleasure of meeting, my name is James Haughom Jr. I was in the SOC over there doing IR for about a year and a few months, and a few months ago I got moved over to the Focus Operations team where I handle malware analysis and reverse engineering, also any forensic cases that are IR related. So here you can find me on Twitter. I just got one, so I'm not that cool. I don't have that much stuff on there. I do try to put at least 1 or 2 blog posts a month for my blog. I have everything on there from really digging into malware. I'll put some SORN YAR rules on there, and then I even have actually, speaking of shellcode, my last post was actually walking through one of these pieces of shellcode we're going to look at today. So if you want to get more in depth than what I'm going to talk about, you can find it on there. So I just wanted to drive home some of those points that that Billy was talking about when it comes to shellcode. So we want to think of it as shellcode as sort of a blob of hexadecimal characters, right? That has to be specially crafted to be interpreted by the CPU. So the shellcode pretty much is representative of opcodes or operation codes. And these are going to get translated from hex into the 1s and 0s that the hardware will actually interpret. So we also have to remember about shellcode that it's position independent, right? So that means it doesn't have any reliance on where it is in memory. Like if it hits the CPU, it's going to execute. That's just the way it's going to work. And then also very, very low level, meaning almost no abstraction. Okay, so how many developers are in the room? Developers, IR, forensic people, reverse engineers, SOC people. Okay, cool. Thank you. And then, like he said, Billy said, so shellcode cannot stand alone. So it has to be injected into a running process. Thank you. Or loaded into a running process, right? The big difference here between the Linux shellcode and the Windows shellcode is going to be Linux. It's going to be a lot cleaner just because the way Linux works, right? You're allowed to make direct requests to the kernel versus Windows. We're going to have to go around the Win API and do some finagling, which we'll talk about in a minute. So as Billy said, syscalls are going to be in 80s, and I'm going to focus on Windows shellcode. And Windows shellcode gets a little tricky just because, like I said, you have to leverage the Win API for your code to run, and then you're going to have to find these modules and these libraries dynamically at runtime. So that's why it gets a little challenging. So shellcode may come in different flavors. You know, you'll find these in Word documents, you'll find them in PowerShell scripts, you'll find them in executables, you can find them literally anywhere. So any of these guys here are valid shellcode. So when we say abstraction as developers is what we're talking about. So if we start at a very high level, we think Python, Perl, right, Ruby, these types of things, and then we go down to where there's almost no abstraction to actually like 1s and 0s binary. Shellcode's going to sit right here, one step above, right? So this is very, very low level programming. These are all hello worlds. Shellcode, a representative of that shellcode, basic C program, and then that's actually Linux assembly right there. So to get an idea how I said how intermingled the Win API can be and how much cleaner Linux is, this is an HTML page being rendered on an Apache web server versus IIS.
Jesus.
So this is a lot cleaner, right? Because we have, you saw Billy's code, int 80, and then you just pass your arguments into those general purpose registers. Over here, we have to use user code, probably some C, more C, Win API, native API, and then we're down to the low-level stuff. So that's kind of what we're working with, and this is kind of representative of analyzing Windows shellcode versus Linux shellcode. So, so as I said, Windows requires the usage of the Win API. We all know an API is application programming interface. If you want to use like our environment, our resources, you have to come and use our native code, right? So if I have 100 domains I want to process in VirusTotal with a Python script, then I'm going to have to use VirusTotal's API. You know what I mean? You have to use your native code in order to interact with that environment. And the Win API is for the Windows environment. So if you want that's what compatibility is. If you want your executable to run in Windows, then you're going to have to use the Win API. I already hit on these guys. So the Win API basically, we can think of it as a collection of libraries, or DLLs, which are going to be in C Windows System 32 on any Windows box. Now, a DLL is a dynamically linked library, which is basically a file that's going to contain functions. It'll provide functionality for whatever process is going to import it. So if these are all my running processes, right? All these guys here.
Yeah, you're no longer displaying.
Oh, sorry about that.
Is this actually just an indictment of Windows, no signal?
Yeah. All right. Well, basically, what I was going to do is I was going to show you a task list, and then I was going to show you the modules, right? So we might have, you may have 10 different modules or DLLs loaded in a process, right? Or 50. You can have any number. So running process on Windows, they import these DLLs in order to interact with the Windows environment. These DLLs export functions, and we refer to them as API calls. So over here, this is a very common DLL that we'll see used all the time called kernel32.dll. And here are some of the common API calls that it provides. So if you want to create a file in Windows, you import this baby right here, and you call create file. It's that simple. So just like we all know a hello world will do printf, same type of deal. Create file, create process, that's how they all work. These are especially popular with shellcode because we have virtual alloc here, which is going to allocate memory in the caller's process. And then we have get proc address, which is going to resolve memory addresses of functions that we want to use. So do we understand that? So Linux is more static. We're able to just make direct syscalls using syscall numbers. And then Windows, we're actually going to have to find this code in memory. Down here, this is also common in shellcode for doing quick callouts. This is just a basic network socket, TCP or UDP sockets for network outs. Down here is a hex view of some exports from a DLL. So this is what I'm talking about right here. So we have create directory, create enclave, create enlistment. Okay, so how does Windows shellcode load its modules, right? How is it going to scrape memory? How is it going to work? How is it going to find the code it needs in order to do bad? So 3 letters, PEB, the process environment block. So this is a very, very, very important data structure that's in user mode, user memory. It's a bunch of metadata, pointers to other structures, as well as it'll hold a lot of environmental variables. So every single running process on a Windows box has a corresponding PEB. And what's nice about it is it sits at a fixed location, right? So in 32-bit architecture, it's going to sit in the FS segment register at offset 30. 64-bit architecture, it's going to be at GS 60. So why is that important for malware authors or shellcode authors? Because even if you have ASLR enabled, does everybody know what ASLR is? Okay, it stands for Address Space Layout Randomization. So basically, it's a way Microsoft implemented it to avoid exploitation. So basically, it randomizes the address of where like executables and DLLs are loaded in memory. So if this same executable, right, if every time I open up calc, it opens up in the same place in memory, I know what I need to target in that exploit. But if it's random, then I'm going to have to find it. I have to do more work, right? So it's to avoid exploitation. So, but the PEB sits at a fixed location, so we can query the PEB and jump to it in order to find the libraries that we need to grab. And again, here's some more information you'll find in the PEB, full command line arguments, the image path to the running process on disk, list of its loaded modules, and the base address. The base addresses of the running process and those DLLs. So that's going to tell us where in memory these models are located. And over here, remember Windows is in C, right? When we think of Windows internals, we want to think about these structures in C. There they are. And this is going to be the important one right here, is the PEB loader data struct. And this is just the sequence of events of how shellcode is going to find the libraries that it needs to resolve the code in order to get stuff running. So it'll locate the PEB, jump to the PEB loader data struct, and the reason being, this is the structure right here. Look at these guys, in load order modulus, in memory order modulus. So there's literally an entry here in this data structure that has a list of all the modules, so that the malware can then iterate through that list and find, oh, here's kernel32.dll. I'm going to grab that and I'm going to use that. Or, as we saw before with WS, with the WinSocket, we want network comms. Oh, here's the WinSocket. I'm going to grab that, now I can use it because I found it in memory. Now once it finds that DLL, it's going to have to iterate through that DLL's exports to find the specific function, right? So if I can just drill this in everybody's heads about Windows internals, we have running processes which are executables. They're going to import DLLs from the system, shared resources, right? And those DLLs are going to export functions or API calls for the running process to use. It's just like in Python, how we'll import OS, import codecs, import base64 or whatever. All right, let's do it. My demos crashed on my Windows box today, of course. So I'm gonna improvise over here. So I'm going to actually walk through a piece of shellcode. So most shellcode that I've been coming across lately is being invoked through PowerShell scripts. So I found a nice easy one that we can use for demo. All right. So let's take a look at it. It's a bat script. Okay. So this is, everybody see this okay? A whole bunch of switches, right? A whole lot of aliases up here. But what we want to focus on is payload, right? We want to focus on what is this big bastard right here. So let's go ahead and grab this. No, because I hate myself, I'm going to do this in PowerShell, which doesn't have like a nice one-liner to decode base64, if anybody's done it before. Okay, so here I just stored the variable, in the variable s, I just stored this big base64 blob, right? Okay, so in Linux you can just like echo, or you can basically echo base64 and then pipe into base64 tag D or whatever. So PowerShell, you actually have to, all the way down there. And in PowerShell, yeah, you have to convert to bytes.
You cybershell.
No, I'm making everybody suffer.
No, you're suffering, really.
Okay, so see, we switched it. We just translated to bytes, right? There's a decimal representation of the hex bytes here. And if we look, every other one's a null byte, right? So we know that this is going to be a Unicode string. So Unicode. Let's get our string. All right. There we go. Okay. So let's grab this guy out and then take a look at it. Okay. Get rid of this. We'll change our language to PowerShell to make it a little prettier. And then we're not going to focus on that. Okay. Can anybody spot the shellcode? Right? Probably all of this crap here. So first, let's just clean it up a little bit, just so we can see what's going on around the shellcode. All right. So whenever you see these brackets, usually indicative of .NET being accessed, C# code being accessed in PowerShell, so that's what's going on over here. But like I said, we want to focus on this byte array. So what I'm going to do is I'm going to extract this. I'm going to dump it to a binary file so that we can then analyze it. We can throw it through a shellcode emulator. We can run a Python script against it to turn it into an executable. We can debug it. We can disassemble it. We can do all types of nasty things to this. All right. So just to confirm, it went. All right. There we go. Now, this is my favorite way of dumping this type of binary. And then just to confirm that this dumped correctly, when we run this, we should see, yes, we should see it's interpreted correctly as binary code, like we have an IP at the end. Okay, so now we've extracted the shellcode. Now we can actually start analyzing it. So as we triage shellcode in an IR, it's often enough analysis to actually just throw it through this tool called SC debug, or shellcode debug, which is a shellcode emulator. Here's this guy. Where is it? Okay. All you do is drag it to the interface and click launch. So it emulated execution, and it's telling us what API calls it observed, right? And it's very much indicative of what we were talking about earlier. The first thing, it needs to load its libraries, right? So we have load library. It load WinINet, which is obviously provides functionality for network comms, specifically over HTTP. And then we have Internet Open, which opens a handle to the internet. A connection request. We have IP here until we actually have the HTTP send request. All of that, and then following it, we have virtual alloc, which is interesting because now it called out, right? Now it's going to allocate memory in this caller process, and then call internet read file. So it's going to read in something from C2 after it's allocated memory. So it's probably a downloader, right? It's probably going to download additional payload and then load it. So sometimes this is enough analysis. If you're in an IR or you're doing some basic triage, this right here is quick and dirty, and it's you'll see after we reverse it, we're not going to find much more than this. We'll be able to look at it at a lower level, but this is handling everything. We have our IOC, we have the actual API calls that were used. Does anybody have any question? Do we understand what API calls are? Cool. All right. So next step would probably be to run it, right? So we need a way to host the shellcode. So there's a really handy Python script out there. I already pushed the shellcode over here, the shellcode.bin. This is called shellcode.exe.py. And this is all you do. And then it basically it writes a little host executable for it. So as simple as that. We have now our shellcode is now hosted in this executable, and we can do like basic dynamic analysis on it, or we can debug it even. So let's go back to the Windows VM, and I already have it over here. This is it right here. Okay, so let's say we want to run it and do some basic dynamic analysis. So here's my procmon filters set. I like setting them process start, reg set value, and write file. This process name will be s.exe. I already have one open. All right. Okay. So we can see through the emulator through SC debug that this that it's going to call out. So we may want to intercept these comms, right? So if we go over to Remnix, we can actually intercept it. So when I analyze malware, I basically have I statically assign like DNS in my gateway from the Windows box into the Linux box, just so I can intercept all the traffic there. Just start a few things up here. Tiny keyboard, sorry. Don't hit me. So let's just go ahead and run this and see what happens. Let's look at process activity first. Okay, so nothing particularly interesting here, right? We don't see any additional processes spawned. We just see the original. Nothing too cool as far as registry modifications, and we don't see any drop files. We don't see anything written to disk, right? So it does look like it's just calling out. Now let's see why it did not capture here. I'm going to switch gears here, and then I'm going to show you guys how to disassemble this. Okay, so we have our way of emulating the shellcode for a quick triage. We have a way of running the shellcode and executing it to do some dynamic analysis. Now, what if we want to disassemble it, right? To actually take a look at its assembly instructions. All right, here we go. So let me pull this up for you guys so we can see the opcodes, right? As Billy said, here are the opcodes, and then here is the human readable version of those opcodes. So here's the assembly language, here's the assembly instructions as we call them, and here are the actual opcodes over here. If we compare it, we can see there's FC, which is clear direction flag, and then E882, which is, it's pretty much a jump, right? A call. And then we have our push A for pushing all the general purpose registers to the stack. So you would handle this as you would handle. I can't teach assembly right now, right? So you would handle this as you would any other piece of malware. Now that it's in this form. One thing that I can do that I would like to show you though is I want to show you how. Because right around here is where it's kind of interesting. This is where Windows shellcode does its thing to sort of find the modules it needs. So let's at least locate or identify what we talked about in the discussion earlier. So we said that the PEB, right, was located at FS30. And if we look right here, we see that value. Oh, you guys can't see that, can you? You see the value FS30. We ignore the EAX because if you look at the instruction before it, it's XORed by itself. So that's just to ensure that this register is clear, there's nothing in it. So this is equivalent to FS30. So we can comment in there and be like PEB. So now it's moving over, and let's think of these over here as variables, right? If we can think of general purpose registers for a second, let's think of these general purpose registers as like temporary variables. So right now the PEB, the location of the PEB was just moved into EDX. So EDX is now our variable of interest. From there, CHEX is being added to it. And if we remember from earlier, that's where the PEB loader data struct is, right? So we can write that in. And then we see one more movement here from the PEB loader data struct to offset 14, which is going to actually be the in-memory load order module list. So now this, if we think of this general purpose register EDX as a variable, it holds a doubly linked list of the current running processes modules. So just that quickly, it found a list of the modules that it can then iterate through to locate the DLLs that it needs. Once you locate the DLL you need, you can then iterate through its exports to find the actual function, right? So let's say I'm iterating through this doubly linked list, and I want to create a process. So I'm going to iterate through until I find kernel32.dll. I find it. Then from that offset, I can jump to its exports, and then I can iterate through its exports until I find create process. So yeah, so this is the disassembler, right? Another little trick with shellcode. Let me see if this one does it. Yeah. So Billy was talking about how, since it's 32-bit architecture, right? So strings have to be passed in 4 bytes at a time. So you'll see things like this. See that? WinInet. That's the DLL that we saw loaded earlier with the emulator, right? So pretty cool. This is very very low level analysis. Super nerdy stuff here. All right, Damien, did you? Damien,
That's why it's backwards.
So, yes, dude, Indianness, because x86 is little Indian. Okay. Yeah. Now let's, the last thing I'd like to show you is how we can load this into a debugger to speed up analysis so you're not just jumping around. Because I actually do want to show you one more thing in here, actually. No, I don't want to confuse you, never mind. Okay. Let's load it into the debugger. And then here we are. So what I would recommend doing in analyzing shellcode like this, shellcode is small enough that you can literally set breakpoints on every single call, right? Because if there's something to occur, then it's because a call was made to the system, right? Otherwise, nothing's going to happen. Memory can move around and stuff, but for actual like I/O, for if there are things to actually happen, there has to be calls there. So I recommend setting calls on all these guys over here. So let's see. So you can step through this, right? And we can just kind of see what happens. We can keep playing around with it. Let me start this up. So before it jumps to this part of the code here, it grabs that WinInet string, right? You can see it down here on the stack. All right, so here's the stack. This is actually a lot prettier. Let me just, I guess I'm talking about the debugger now. So down here we have the stack. Over here are our general purpose registers, as Billy talked about earlier. And right here is our instruction pointer, which all its job is to point to the next instruction to be executed. And we have to remember that the CPU is going to execute instructions like this. It's going to be in order unless it jumps around. Down here is a hex dump window. And like I said, up here is these are actually the instructions. I'm going to set a breakpoint here to show you guys some stuff. Okay, and then I'm just going to start running this. Okay, so I set a breakpoint here, jump EAX, because that looks interesting to me. Why? Because I've seen this before, right? A lot of the shellcode gets recycled over and over. There's only so many ways to skin a cat and load your freaking shellcode into Windows, just because it's such a pain in the ass to find all your stuff in memory. So what I found in analyzing shellcode like this, because this is actually, I think this is Metasploit Venom generated shellcode, and everybody uses it. Everybody from script kiddies to people like APT. So do you guys remember that CVE that was released a few weeks ago for the that Flash exploit? Yeah. So their shellcode looked exactly like this, even though it was by an advanced actor. Okay. So when I said breakpoint earlier, what a debugger allows you to do, right? We are controlling the flow of execution of this malware. We are manipulating it at a very, very low level. We can literally step through this one instruction at a time, one line at a time. So breakpoints allow us to stop the program, and we can set breakpoints on specific instructions. We can do it on when a certain part of memory is accessed. We can do software breakpoints on like specific API calls. It's a very, very powerful and useful tool. So we have here a jump EAX, which again I think it's going to be interesting because we're jumping to a location that's that's not brought up or doesn't resolve until runtime, right? So at runtime, EAX is resolved, and then look what it represents: load library, which is the first API call that we saw loaded in scdebug. So now what I did was I stepped into that function. So no longer am I in user code, now I'm actually in that DLL up here. And if we look down at the stack, there's WinINet. So load library is an API call that's used to load a DLL or load a module from C Windows System 32, right? Well, really it can be anywhere, but that's where it's going to look. And it takes one argument, and that one argument is the name of the DLL. So here we go, we're loading WinINet. Let's run again, see where it takes us. And then boom, we're now at Internet Open A. So this is going to open a handle of the internet for us. I'm going to run again, Internet Connect. Do once more. And then we actually have, and here we have the rest of the URI. And there we go. And this is going to be the final one to actually send our HTTP request before a response is read, and then whatever bad the shellcode wants to do with it after that. Does anybody have any questions? I know Windows internals is kind of a pain.
Are you seeing a lot of IP addresses statically assigned in the shellcode, or are you seeing a lot of domains?
They're always going to be statically. So malware will always, so I'll say this: malware will always statically or hard code. It will always hard code the C2. The only time it doesn't if it hard codes a domain generation algorithm or a DGA. You got me? So either way, we know what you're going to do. You're either we can either pull out your list of C2s that you've hard coded, or we have your domain generation algorithm, which we can probably decode ourselves. And those are pretty interesting.
We're monitoring those DGAs going through your DNS servers as a way to detect that kind of traffic, right?
Yeah, and once you have the algorithm, you have the algorithm. And if you've seen it, if the host beaconed out, then you should be able to take, usually they'll use something like the day of the week, or a time, or something, some variable that you can just grab out of nowhere. But yeah, so it'll always be hard coded though, pretty much.
Back to the dynamically linked list. Was that or is it use like a binary search function or something?
So either doubly linked list or
the doubly linked
dynamic linked library, which
doubly linked list you had that was going through the list of actual modules.
Yeah.
Was that does that use like a binary search or something?
No. So basically, how can I show this? It's just a simple, right? So we have to think of Windows, like I said, in C, right? This stuff's written in C. So a doubly linked list is it's a very simple data structure where you have a forward link and a backward link, and they just point to each member. So here you'll have like kernel 30, like this is popping up here. So you'll have ntdll.dll, kernel32.dll, kernelbase.dll, advanced API.dll, just like that. So what it'll do is, because these are just pointers, they're just 4-byte addresses that point to the next one. So we can just like sort of increment by 4 bytes to go to the next one. Does that make sense?
Yeah, it does.
Okay. Okay.
For somebody that's more ignorant of threat acting, how do you go about getting somebody to execute shellcode?
So, there's tons and tons and tons of different ways. I think, so for example, right, so let's say that I have shellcode like this. This shellcode, to me, this is a downloader, right? This would be very useful for me to send an additional payload. So I would use this as delivery malware. Now, what would host it? I would probably drop that into an RTF file, right? Because it supports OLE objects, which can handle that binary. That binary data and execute it. So I would send that in email probably. That's one simple way. A stupid user will open it, as they always do, and then it'll cause the shellcode to run.
But ultimately, somebody has to like open something.
Yeah, well, right.
Well-
Something has to be.
Right.
It takes some type of interaction or go into a bad website.
Right.
Yeah, so like there's like James was saying, there's a lot of different ways you can go about it. You know, kind of like I had talked about in my talk. Another avenue where you don't necessarily have to have interaction is if you have an exploit that you're developing or you're exploiting. So like, you know, a common one from the past has been FTP server and the commands like, you know, make directory or something like that may have a buffer overflow. You know, it's only expecting a certain number of bytes, but it doesn't. If you give it more, it doesn't know what to do with it. That overflows into memory, and then you have your shellcode that you have in memory. You control where EIP points, and you eventually somehow get to that shellcode that you had. So that's one way. But you know, like James was saying, you know, phishing, bad website.
And I feel like I've done a small amount of learning about like remote code execution, I think at a higher level. So I guess I was just confused at how you get, this is just a lower level of that, I guess. Yeah.
Yeah, this is this was probably a lot. I mean, this was a lot to sort of jam into however long I just talked. But you know, I wanted to make it more. First of all, I wanted to make it apparent. I mean, that the emulator we ran it through, that was not hard, right? We all can do that. We all we did was have to decode base64 and then drag and drop this binary file into that little GUI, and then it literally told us everything, the same shit we just found out from debugging it. You know, doing it at, you know, kind of makes this level of analysis, it made it almost unnecessary, but we wouldn't know the inner workings of the malware truly until we did look at it at this level. So this is where we can actually tell, does this person know what they're doing? Where did they get this from? Where have I seen this before? So at this level, we're talking TTPs, we're talking some really sexy, interesting, nerdy things here. So.
That's why I named it S.exe.
Exactly. Yeah, so also you'll see a different perspectives here. So Billy, I've written a little bit of shellcode. Billy's written significantly more shellcode than I have. But I look, you know, we both reverse, but I'm probably more so on the blue team side of the shellcoding than he is. So you're seeing two things. That's why he's talking a lot about exploit, and then my mind is going more towards reversing this stuff. Any other questions? Anything?
I know this. How many Java rules would you generate?
How many YAR rules? I don't know. It's tricky with shellcode, right? Because like Billy was saying earlier, I mean, it's when it boils down to it, it's just hex. We can't build YAR rules off these API calls. They're legitimate. Now, what we could do is no, that wouldn't work. I was gonna say, so if you did YAR rules for like maybe for pattern matches, right, on some of these API calls present in a document, why would this RTF have HTTP send requests in it? But look how it's being passed. It's being passed as hex directly, right? So it's that wouldn't be effective right there. There are some signatures that you, yeah.
Just a simple question. I haven't done malware processing on Windows in a while. When you're looking at the export table, is that just a piece of malware that's compiled that has that stuff, or if you've got an RTF document, can you look at that and see what's in there?
So when you export,
I've completely forgotten because it's been like.
so export table, so exports, right?
That's just in the compiled DLL, right?
Correct. So, or .exe, either one. So, but yeah. So as far as functionality, DLLs, yeah, they have an export table. Well, they both. Okay, so a .exe and a .dll, as far as format, they only have. There's one bit flag that makes the difference. Where the true difference is the context and the functionality. So executables, like this guy, right, will typically only have one export, and it'll be the main function. If I go to, let me get in C Windows here. Sorry, I usually type on a much bigger, nicer keyboard than this tiny ass thing. And let me grab one of these DLLs. This is a good one. Where's Ida? Oh my god. Workaround. There you go. So this one should have, yeah, there we go. So this is a DLL, right? So I guess I was a little bit confused because RTFs, right? They're not going to have an import or export table just because they're not PEs as far as file format. But this is the true difference, right, between DLLs and executables. Now these will also have some imports sometimes, which is kind of interesting. You will see DLLs import other DLLs, right? This giant mess of windows. Any other, was that good, man?
Yeah, that was
Okay.
good.
Any other questions?
What I guess differences when you're analyzing 64-bit shellcode?
So it's not that different. You just have to we have to understand, right, that like the arguments are passed differently. We didn't talk about that much today. It's hard to fit all this in. And as long as you understand like the big thing, right, is like where the PEB sits. The PEB, the process environment block, just because that's where in Windows shellcode that's where the malware is going to go. And also Linux shellcode, I haven't really looked at much. 64-bit shellcode you do not come across it much. So when you do it, there's usually you can usually pinpoint some things.
And like one of the things you'll run into, and because you don't see it as often, is some of the tools that you're used to using don't work on it.
Yes.
And we've run across that before, and then you just kind of have to start going manually with it. But like you were saying, where things are sitting in memory is different, and then the instructions themselves are different, but usually they're close, or more so the registers are different, but they're usually close enough that as long as you know what to expect, you can find it. Like EAX is RAX. And then the other thing to keep in mind is when you are working with a stack, or you're seeing something work with a stack, you've got 64 bits of data instead of 32. And so you have, I can't remember how RAX is broken up, but it can break up like EAX can, but you have more pieces to work with.
Yeah, definitely not something we see often, just because usually malware authors are greedy and they want to run across all, they want to pwn everybody they can. So why limit yourself to people that stay up to date?
And just to kind of to build on the question earlier about like where you'd see it in attack. Like one reason why you do shellcode instead of just here run this executable is rather space, simplicity, or sometimes just evasion. And my guess is probably why like we're seeing more things that are in like PowerShell running shellcode and stuff like that. Because if you have a blob of base64 that's a executable, you'll see that in Z header. That's a flag. A lot of things flag on that. Whereas if it's just instruction, like James said, it's hard to pin that down of is this actually instruction? Is this legitimate instruction? Stuff like that.
Well, going off of that, right? So if we have PowerShell logging is real now, right? PowerShell logging is awesome, and most people are getting it. Most people are getting it in the SIM. So if I have detections built around like risky PowerShell commandlets or arguments, if I'm looking for IEX, if I'm looking for encoded command, I already said invoke expression. If I'm looking for anything weird like that, those can be strong indicators. But I don't know that I'm going to be looking for a byte array. Like I don't know if I'm going to be looking for specific assembly instructions in the PowerShell logs. So that also might be another reason.
I don't know if you just answered my question or not, because I don't really work with PowerShell too much. But I was thinking, what if you had like a USB key that was a human interface device, one of those things that like emulate keyboard presses when they're pressed, and you just like launch a PowerShell window.
Rubber ducky?
Yeah,
Yeah.
that thing. You just launch like a PowerShell window, and then macro, you just type all that stuff out and execute it.
Yeah, I mean that's definitely something you could do.
Yeah, I don't know if it's gonna
Yeah, it's still running.
Yeah,
it's still a thing. It's just it's a macro instead of the asshole at the keyboard.
Yeah.
Never actually used one before.
Is there an acronym for that?
Nothing else? We can keep just nerding away. I love this.
All right, thank you guys. Appreciate it.
Yeah.